Hello, welcome to our monthly LHS Collaboratory seminar. This is a seminar organized by the Department of Learning Health Systems at the University of Michigan, which focuses on putting data, knowledge, and practice into motion at the University of Michigan. But we invite a broad audience to come to this, and so we appreciate your attendance today. Today's session, we'll be talking about the issues of explainability, artificial intelligence, and ethics. Explainability has been called out as an important feature for artificial intelligence models and something that needs to be a requirement for us to be able to use artificial intelligence ethically. Today, I'm really delighted that we have two speakers who will be able to talk in depth about both the advantages of explainability and its limits in trying to use artificial intelligence ethically. Thank you again for everyone in attendance. I wanted to go through a little bit of housekeeping before we get started. Today's session is being recorded. The recording link will be shared with all attendees and registrants. This session will be live closed captioned. And there will be two different ways that you can share comments. First, if you have questions for the speakers, please post them in the Q&A pod, which will be enabled throughout the session. We'll also have the chat pod open. So I'll be monitoring both the Q&A and the chat so that towards the end of the session, when we have our moderated Q&A, I'll be drawing from questions in both places and presenting them to our speakers. So we have two wonderful speakers today. Alex John London is the Clara L. West Professor of Ethics and Philosophy and Director of the Center for Ethics and Policy at Carnegie Mellon University. He's an elected fellow of the Hastings Center, and his work focuses on ethical and policy issues surrounding the development and deployment of novel technologies in medicine, biotechnology, and AI. Melissa McCradden is a bioethicist with the Department of Bioethics at the Hospital for Sick Children, which is also known as Sick Kids and affiliated with the University of Toronto. In her role, she provides clinical and organizational consultation, gives education to staff and trainees, participates in and leads policy development, and conducts research, and is the director of AI integration in medicine at the Hospital for Sick Children. We'll start off with both of the talks, and then we'll end with a moderated Q&A session. So without further ado, I will turn it over to Alex.
Okay, thank you very much. Well, first of all, thanks to the organizers for inviting me, and thanks to Dr. Singh for that introduction. Sorry, I just want to share my screen. Okay. All right, so I'm going to be talking about structural challenges to AI in medicine, and why I think explainability is really not the solution. So I think explainability is fine as far as it goes, but part of the talk is about, well, how far does it go? So I'm going to talk about some benchmarks for responsible innovation. I'm going to talk about explainability, interpretability, and how they're pitched as solving problems that are sort of central to responsible innovation. And then try to say why I think there's a relatively limited role for explainability or interpretability. I'm just going to talk about explainability. I'll use those terms as synonyms, even though I know some people use them to refer to quite different approaches. But I think there's limited role for these in meeting the goals of responsible innovation. And I want to suggest there's a greater role for changes that need to be made in aspects of AI system development that are kind of outside of models. And that these changes are really needed to unlock the potential for AI in medicine. So I'm going to start just by saying that addressing uncertainty in medicine is a really important ethical imperative, that there's a prima facie duty to carry out research that has social value, where that means it generates information that's necessary to meet important health needs, to reduce medical uncertainty, and reduce unwarranted variation in practice, and that this imperative derives from the importance of health systems being able to function effectively in terms of advancing patient interests, efficiently in terms of stewarding scarce resources, and then equitably in terms of functioning equally well for all of the people whose interests those health systems serve. So 3 benchmarks for responsible innovation then is that we want this process to produce credible public assurance that innovation is enhancing the capability of health systems to advance patient interests, steward scarce resources, and function equitably. We also want credible assurance that the parochial interests of the various parties that operate within this system are either constrained or aligned with these patient-centered outcomes. And in particular, that patients are free from domination or manipulation or exploitation. So explainability is usually pitched as playing a pretty important role in this process. So this is a quote from a paper where they mention a lot of the things that I'll sort of talk about in my talk. So I don't want to paint this paper as sort of overly relying on explainability. I think they give a nice picture of what people expect from explainability. But it's also kind of an afterthought in the paper. And in a certain sense, I think a lot of the appeals to explainability in this space have this kind of feeling of, well, I have to say this, but I'm not sure how much I believe it. So they say healthcare offers one of the strongest arguments in favor of explainability, given the combination of the devastating consequences of unacceptable results, the high risk of unquantified bias that is difficult to identify a priori, and the recognized potential for models to use inappropriate confounding variables. Explainability enables system verification. This improves expert ability to recognize system error, detect results based upon inappropriate reasoning, and identify the work required to remove bias. So they go on, but I think these 3 ideas, recognize error, detect inappropriate reasoning, remove bias, those are all mom and apple pie, right? Those are super important things. My first worry, though, is that explainability and interpretability are relationships between systems and stakeholders. They're about how well stakeholders like clinicians understand how the model works. So maybe which features it uses, and then how it uses those to produce an output. The things that we care about from the clinical standpoint, though, like the accuracy of a model, its efficacy, whether the task performs has real clinical or social value, those are relationships between systems and the world. And a theme of this talk is that explainability, better understanding of how your model works, can't bridge the gap between model and world. So I want to say a lot of major ethical issues, including some of the ones that we just talked about, they arise from dynamics that occur outside of the model. And they may not be detectable from a better understanding of the model, and they may not require a detailed knowledge of how the model works to detect and address those problems. So a big problem is that AI systems develop out of and feed into health systems. And so dynamics that occur before model development and after model development have an important sort of role in affecting the kinds of problems that we're talking about. So for instance, whether the task that we design an AI system to effectuate is going to advance important health needs, that's a relationship between the AI system, its capabilities, the capabilities of the health system into which it would be embedded, and the needs of patients that the system is supposed to advance. A special concern in medicine is that there's no guarantee that the data that we have, routine clinical data, will support models that perform tasks that will make health systems more effective or equitable or efficient. So the theme now is about the tasks that AI systems perform. And if you're creating systems on the basis of the data that you have, then there may not be an alignment between the data that you have and the tasks your systems can perform. So if we go back the heady days 5 years ago, where the sort of proponents of cognitive computing were saying, the goal of cognitive computing is to create automated information technology systems that are capable of solving problems without requiring human assistance. So the Watson group, Watson had just sort of conquered Jeopardy, and they were like, we're going for the brass ring. So they chose tasks where they wanted the AI to function sort of independently of the person. Now, conversely, people had said, doctors would have been delighted to have an AI librarian at their beck and call, right? And so if that's what IBM had originally promised, they might not have been so disappointed today. But the story of Watson Health is a cautionary tale of hubris and hype. The hype here is reflected in statements like this, where people said, new AI systems that augment the role of doctors and engage patients will expand access, lower costs, and most importantly, improve outcomes. Now, expanding access, lowering costs, and improving outcomes, that's what we want. Those are the goals that we want out of responsible innovation. But this will here is really ambiguous. How is it going to happen? It's not guaranteed. And the idea that AI systems are going to lower costs is sort of belied by the fact that you have places like MD Anderson. They canceled their project in 2016 after they'd spent $62 million on it. It's not clear what value they got out of that investment. And Watson itself was recently sold for about $1 billion when acquisition costs alone had been about $5 billion. There were 7,000 employees involved on the project at one point, and commentators said it's a total failure that they needed to just cut their losses and move on. Watson is an example of a real-world, large-scale initiative to use AI to effectuate the goals of responsible clinical development. And part of what it foundered on was a mismatch between our understanding of what these systems can do, the data that's available, and the task that was chosen for them. Even if we do a better job at task formulation, we still need data that's fit for research purposes, because our models are going to be built out of that data. And another structural problem with healthcare is that data reflect the purposes for which they're gathered. So which variables are measured, with what frequency and what granularity. Often that reflects purposes like billing or other clinical goals, rather than the goals of learning. In medicine, the data sets that we have often reflect multiple confounding factors, including the large-scale effects of broader social systems and the way that patients are treated within the health system itself. So, as you know, our health systems in the United States are very inequitable. This is reflected in genetics databases, where in 2016, about 3% of genetics databases were populated with samples from people of African descent. So not to essentialize race, but just to say, if there are genetic characteristics that vary from populations of different origins, and you have a high representation of white European populations, and you have a lower representation of other populations, then genetic differences are going to that vary across these populations won't necessarily be represented in models that we develop from this data. And increasingly, medicine is relying on this kind of data for understanding of disease etiology and drug development. A more recent example of the effort to develop a deep learning system for differential diagnosis of skin disease. If you look at the table, so these are Fitzpatrick, these are examples I got from BMJ of Fitzpatrick's skin types. And, if you look at type 6, there was one person in the validation set and there was nobody in the enrichment set. We also know in the United States that disparities in social determinants of health produce disparities in the health status of people. And those disparities have often been treated as biological differences among people, rather than as via some colleagues say, injustices that require intervention. And so this is a lovely article that goes through race corrections in many, many, many disciplines, and explores the way that they use differences in the health status of patients to have race corrections that often work to the disadvantage of Black patients. The point here is that social and structural determinants of health have a dual impact. Disparities in the ability of health systems to advance the needs of all groups perpetuate these disparities. We see this in bias in devices. We see this in race corrections and algorithms. The effects on health systems on patients, though, are part of routine clinical data. Those effects are reflected in the data that we have of patients, and those are the data that we want to train AI systems on. So building models from this data can perpetuate or exacerbate some of the health inequalities that are in the systems in which these systems are, these AI systems from which they're developed and into which they would be embedded. All of these issues reflect what the authors of this wonderful paper, Everybody Wants to Do Model Work, Not the Data Work, refer to as data cascades, compounding events causing negative downstream effects from data issues that are triggered by conventional AI or ML practices that undervalue data quality. So in healthcare and in other, so the authors of this paper talk about high stakes learning, high stakes applications of AI and how data gathering is often neglected. And part of the allure of AI in medicine is the allure for cheap learning. And so many of the variables that they describe that can lead to data cascades also appear in medicine. You have, as in the Watson case, clients that expect magic from AI. So you have then data acquisition, curation, and preparation, not necessarily at the forefront of what's budgeted for. These things are often regarded as arduous and thankless tasks that are not necessarily the path to future employment. But these sort of high stakes contexts often require bespoke data. And so there's a sort of unpreparedness to create pipelines that get the kind of bandwidth, granularity, and specificity of data that you need to build these kinds of bespoke models. Well, all those problems are upstream now to model development. And so you might say they're not really relevant to explainability because explainability is about our relationship to models. And one of the goals of explainability is that it can help us validate models and understand and avoid some of these problems. So I want to be cautious about that, though, too, in particular, because some of the problems that we encounter with models aren't necessarily the result of their opacity, but they're the result of our wanting them to do things that they can't do. So current AI systems are good at performing two general classes of things, classification or diagnosis, and then prediction, where we're saying something like, what's the probability of an outcome given a wide range of variables that I've measured in a system, assuming that that set of variables largely stays the same. If you are an insurance company and you care about actuarial things, then prediction is really great. But if you're in a healthcare provider, medicine is often ultimately interventional. You don't just want to know what's the course of care for somebody likely to be if things continue the way they normally would. You want to intervene to change the course of care. So you want to say something like, well, what's the probability they will have a better outcome if we force some measured variables? So we change their blood pressure, we give them surgery, we give them a drug, we force that variable to take some other value. Well, transparency is supposed to be, let me give you an example now where I think a mismatch between what a system was trained to do and what it was used to do was really the underlying problem. But it's given as an example where explainability is seen as the solution. But I'm not sure explainability really is the solution for this. So Caruana and colleagues have this famous example where they talk about probability of death from for patients who have pneumonia from medical records. So here's our interval from 0 to 1. And in this setup here, the line is the patient. So this is a patient that has pneumonia, this vector of characteristics, and asthma. So this is a particularly sick patient. This patient has pneumonia and similar characteristics, but doesn't have asthma. And so what you would think is that this patient would be sicker, a higher probability of death than this patient, would have a higher probability of death because they're sicker. What Caruana and colleagues saw when they looked at a bunch of AI models that they had trained was that those models were saying, hey, the asthmatic has a lower probability of death than a non-asthmatic. And they use this to say, this is a reason why we want to have explainable models or transparent models. We should prefer simpler ones, even if they're less accurate, if they're more transparent. Why? Because, well, we can detect a problem. We could go in and we could change the weight on asthmatic and help it to avoid this error. But was that really an error? The problem is the question that that system, my mouse is too sensitive. The problem that the question that system was designed to answer is something like, what's the probability of death given the things that we've measured against the background of current practices? And there were many things that weren't measured in that study. For instance, that patients with asthma who are very, very sick were immediately given much more intensive care than patients who didn't have asthma. That system was actuarially correct. As a matter of fact, the way that the healthcare system actually functioned, patients with asthma were at a lower probability of dying than other patients. But this system can't tell you the counterfactuals that Caruana and colleagues wanted to know. They wanted to know something like, sorry for the typo, who is the sickest patient independent of healthcare? And maybe how could we better allocate healthcare resources in order to meet those needs? But those counterfactuals can't be answered by this system. So understanding how a system uses features to arrive at an output doesn't necessarily entail the ability to use that model for tasks for which it was not trained and not empirically validated. And so a worry is explainability can lead people to think, because they understand the model and they have intuitions about how the model should work, that if they change it, they'll make the model more accurate. But that's a question about the relationship between the model and the world. I think a very similar thing goes on in this paper by Obermoyer, where they talk about a system, Optum's Impact Pro, where it could predict the costs given standard practices for different people. So if you're admitted to the hospital, it could give you a forecast of what's the cost given, features of the person who is admitted. But then what healthcare providers wanted to do was intervene on the sickest in order to improve outcomes. And now the problem was it wasn't validated for that task, and key assumptions needed to perform that task were not really evidence-based. So it turns out that stratifying patients in terms of their costs, because of these structural differences in access to healthcare, meant that white patients were usually healthier in every sort of cost strata. And so stratifying the healthcare that you would give to patients by cost meant that you were allocating disproportionately healthcare resources to healthier white patients and deprioritizing sicker Black patients. Did you need to see the model in order to understand that, or was it could you have focused on the data the system was using as an input and the task that it was being used to perform? What about the extent to which transparency or explainability helps with model testing? Accuracy, as I said, efficacy, clinical value, the relationships between systems and the world. So when your model captures the relevant causal features of the world, explanations that derive from that model can detect and avoid error, they can improve reliability and efficacy, and they can even obviate the need for trials or empirical testing. That's true in some domains. So structural engineers are really fortunate. They have very comprehensive models of relevant features in the underlying causal systems when we're talking about things like building a bridge. So they understand how soil composition and weather and climate and material tensile strength, durability, and the structural capacities of alternative designs will affect a structure's ability to bear certain loads under various use cases. And so they can simulate models, they can engineer to cost, and then they can reliably build a single bridge. They don't need to go out and build a whole bunch of bridges and see which ones, in real life, which ones fall down or not. But that's because we understand the equations. The models that we have model the features in the world that are causally relevant, that kind of cut the world at the joints. Another problem in medicine is that the theories and the knowledge, what we think of as knowledge in medicine, are frequently incorrect or incomplete. So there's lots of anecdotes for this. The idea that radical mastectomy would be superior to lumpectomy, the idea that peptic ulcer disease was caused by acid in the stomach rather than H. pylori bacteria. But if you want more systematic evidence for this, just think about the fact that randomized controlled trials are the slaughter bench of optimism for theories of disease pathophysiology and drug development. 9 out of 10 new drugs fail to win approval for any indication. That's far fewer in some areas like neuroprotective agents or Alzheimer's and Parkinson's disease. And half of what we put into the pipeline fails at phase 3 after you've had, what you think of as positive earlier, results earlier on in testing. Nobody spends hundreds of millions of dollars backing a novel drug that they think isn't going to work. But 9 out of 10 things don't get approval for anything. So I think this illustrates the gap between the maturity of our knowledge in medicine and the maturity of our knowledge in other places like structural engineering, where explainability can obviate the need for rigorous empirical validation. So when our knowledge of the underlying causal system is incomplete, explainability doesn't bridge the gap between the model and the world. So our expectations can come apart from what actually happens, and our predictions may not be a good guide to intervention. And so as a result, I don't think explainability is sufficient for responsible innovation. In medicine, additionally, proof of efficacy often precedes our understanding of mechanism. So we could use aspirin or lithium aspirin as an analgesic or lithium as a mood stabilizer for decades before we understood, if we do now currently understand, the mechanism of action by which they work. But our inability to explain the mechanism of action for those drugs didn't undermine our ability to use them in responsible clinical practice, and it didn't undermine our ability to secure informed consent from study participants. That's because responsible clinical practice, clinicians need to be able to explain things like, what is the patient's clinical situation? What is the indication for this intervention? And so in that case, that would be, what is the very specific task this AI system is supposed to perform? What is the warrant or the evidence that we have that that system will be safe or accurate or effective? And what's the warrant for the claim that this intervention in this context, using this intervention in this context, will replicate expected safety, accuracy, and efficacy? And then can we explain to the patient what the relative risks and potential benefits are of alternative courses of action? We provide that warrant, this warrant for safety, accuracy, efficacy, and the window within which medical systems perform well or not in medicine with prospective, rigorous clinical trials. We test interventions on patients with particular health characteristics under determinate clinical care circumstances. We don't really do that for AI systems. So these two systematic reviews talk about how there are few prospective trials. Performance measures are not clearly linked to meaningful outcomes. Very often, trials that are done are at high risk of bias. In this review of AI to detect or prognosticate COVID-19 from chest radiographs, they say in their current reported form, none of the machine learning models included in the review are likely candidates for clinical translation of the diagnosis or prognosis of COVID-19. And this is not just a problem, this is also a problem in the way that our regulatory system has sort of lagged behind for AI systems. So Wu and colleagues here in this review, they note that none of the 54 high-risk devices that they had evaluated that had received FDA approval were evaluated by prospective studies. And among 130 devices that they analyzed, 93 did not have publicly reported multi-site assessments included as part of the study evaluation. So my point here is, I think we need to strengthen the extent to which we evaluate AI systems empirically under real-world circumstances, and we shouldn't think that a better understanding of the model is going to be a reliable guide to being able to assure their safety and efficacy in clinical practice. I'll end just with the fact that it's not sufficient for you to get the ball to the 10-yard line. You really have to go all the way. And so in order to get real clinical value for patients and health systems, you have to train, monitor, and be able to update your system. And in this paper from Maria de Arteaga and other colleagues from Carnegie Mellon, they looked at call screeners who use an AI system to identify high-risk cases They looked at a period of time when a programming error was introduced accidentally into the AI screening algorithm, so that now the algorithm was getting incorrect assessments. And they asked, did screeners compensate for this or not? And it turned out screeners did compensate for the programming error, in part because they had access to the original calls and the original data, and they had some experience in call screening. But they also say, and this is more speculative, but they noted that the AI tool in this case only provided a score. There was no explanation. And so their worry was, had it been accompanied by an explanation, would that have been more compelling to call screeners, and would that have led them to be less reliant on their own judgment in trying to contextualize the outputs of that system? I'll end here. I know Dr. Singh is one of the authors of this, so I'll just ask it as a question. So this is a piece of local research. They say being able to rapidly assess and disable AI-based alerts is a responsibility faced by health systems using AI to support clinical care, given the susceptibility of AI-based systems to changes in alerting patterns. Clinical AI governance within systems may play a role in monitoring, supporting AI development systems. This was taking sepsis alerts offline in the face of the distribution shift, where you had so many patients with COVID that came in that you couldn't really trust the alerts anymore. So I think that's sort of a good case where people would say transparency would play a really important role. And I'll just sort of ask, and Dr. McCraden or Dr. Singh can sort of weigh in about the relative importance of transparency there versus some of the many other things that we talked about so far. So my conclusion is that structural problems in the relationship between AI development and health systems are a major impediment to the success of AI in healthcare. Addressing these issues requires changes to broader practices, including more rigorous prospective randomized trials for AI systems. And interpretability and explainability, they're great if you can get them, but I think they have a limited role to play in addressing the most major obstacles to unlocking the value of AI in healthcare. So with that, I'll say thank you, and I'll now hand the stage over to Dr. McCraden.
Perfect. Thank you so much. Okay, so I am going to dig in a little bit more deeply into the notion of explainability. And I'd like to really question the presumed relationship between explainability and ethical AI. So just to kind of cover what I'll talk about today, I'll first talk about some of the ethical motivations for explainability in medicine, the practices and provocations, and then explore the ethics of explanations in a healthcare setting. So generally, when I'm talking about explainability in this presentation, I'm referring to two different types. So one is how the model works as a system, and the second is how it arrived at a particular prediction. So post hoc explainability, and really I'm going to focus on that last one. So these two levels of explanation serve different goals. The model level explanations can help us understand the system as a whole and query potential issues regarding patient safety, confounders, validity, etc. And that second level, the prediction level explanation, really is intended to help the user decide if the prediction itself is reliable in this case. And so I won't go too much into detail because Professor London has introduced this study already, but just to kind of reiterate, the motivation for this came from this study by Rich Caruana and colleagues, where they observed that a pattern that could be quite problematic if replicated in clinic, which would be the deprioritization of patients with asthma, was only revealed by using interpretable methods. So it led to the recognition that we need to understand something about how machine learning systems are working as a whole to do some amount of verification as to whether they're working reasonably and whether the patterns that they're operating off of are things that are desirable in practice. Because clearly from this study, we recognize the implications for patients in this setting. Other uses of explainability include things like exploring for hidden stratification. So this is by Lauren Oakton Rayner and colleagues, where they've demonstrated that when you dig into how a model performs, even though generally you use one kind of metric for the AUC, when you disaggregate the performance, you can actually find clinically meaningful performance discrepancies. So in this case, they found that there's a pretty big difference between the model performance on patients with a chest drain versus without a chest drain for the detection of respiratory conditions. And that's really important because having a chest drain typically is part of a treatment pattern for someone with a respiratory condition. And so if the model works better on the patients who are already being treated for a respiratory condition, obviously that's very, very different from the ones who have not yet been diagnosed with such a condition. So there's some pretty serious implications for patient safety in this case. The other use case is fairness. So again, because we often report model performance as overall accuracy, it can mask relevant discrepancies in the performance characteristics of the model along the line of protected identities. We know now that unfairness is prevalent within medical AI. And so some level of explainability permits the exploration of the model's functionality to identify patterns of discrepant model performance. So people have had various ethical arguments in support of explainability. Some have gone so far as to call it a necessary fifth principle for medical ethics. People have posited that explainability helps us address medical legal accountability. So through things like resolving physician or computer discrepancies and trying to figure out who's right and who's wrong in a given case. People have also said it's necessary for informed consent. Professor London talked a little bit about that, and I'm going to go into more depth later on in the presentation. But people have also said that it's necessary for ethical practice. And I even encounter this at the hospital anecdotally, where there's just this presumption that these systems have to be explainable in order for a clinician to use them. So to the contrary, there are criticisms of AI as well. So people have pointed out that computational explanations are not always actually relevant for clinical decisions and don't always reflect the metrics that a clinician really cares about. So sometimes what clinicians actually want is the prediction to be accompanied by the patient's history or some aspect from the patient's chart. And so that doesn't actually require machine learning to deliver that level of enabling understanding of the prediction. And so again, some of these explanations don't actually require machine learning. Some are about human-computer interaction or engineering, so presenting things side by side on the screen, or the way in which a prediction might be delivered to a clinician. Now, one of the big concerns that people raise with explainability is that of overtrust. And this is the propensity to act following incorrect outputs of AI. This has been noted particularly when there's user uncertainty, when there's task complexity, and specific clinicians might be more likely than others to overtrust. And it's also important to say that these risks aren't restricted to black box systems alone. They have been identified in association with more transparent models and outside of an AI context as well. And so if opacity was really the problem here, then explanations would prevent people from acting on wrong outputs. However, this isn't what appears to be happening. And I'm going to give some examples here. So is the black box really the problem? So one of the first cases here, and this is a study led by Dr. Marzi Gassemi and colleagues. And what they did was they looked at, they presented clinicians with X-ray reports, and they were randomized to being either from the advice source of Chest AI, so an AI-based system, or an expert radiologist. So what they found was that there was a negative overall effect from receiving incorrect information, whether it was from an AI or an expert radiologist. Obviously, radiologists less so than internal or emergency medicine physicians. But what they found was that some clinicians were highly susceptible to incorrect advice, whereas others were not. So some rejected every incorrect prediction, and others took up every incorrect prediction. So there's something about maybe the philosophical orientation that people have toward AI systems when accompanied, especially with something like this, where you have a list of the findings that have purportedly contributed to the advice that's being received. This paper actually came out a few years ago. This is a model that predicted 7 distinct types of skin cancer. And this graph on the right here is actually, it's sort of one of the smaller graphs. But what you see is the comparison here between the correct AI predictions and incorrect AI predictions. And so what they found was that when the AI predictions were correct, clinical accuracy improved. When they were incorrect, clinicians were quite often misled. And they were able to do this analysis because they directly compared the pre-prediction diagnosis compared with the one that was the final diagnosis after receiving the AI advice. So they found that changing one's mind was correlated with their pre-prediction confidence, not unsurprisingly. But what's interesting is that you can see here that it's across the clinical spectrum. So all the way from 1 year to 3 years to 5 years. Now, another example here, this was by Maya Jacobs and colleagues, where what they did was they simulated a machine learning model that was intended to make a prediction of what medication a patient should receive who had depression. And so they simulated this model by having an expert ranking of different antidepressants for particular patient scenarios. And so in their survey, they systematically varied the patient scenario, the prediction accuracy, and the explanation. And they compared a number of different types. So in one condition, people saw no explanation. In another condition, they saw the ICD-10 code, so the diagnostic code for depression. In another condition, they had a very generic recommendation. So it might be something like, in patients with lethargy, do not prescribe medications which have sedative effects. And then in another condition, they had what you see on your screen here, which is patient features. So it's called a feature level explanation. And what it purports to offer is the specific features about this patient that are why the model is making this medication recommendation. So what they found was that any explanation at all increased the likelihood that a clinician would follow a model's incorrect prediction. And they found that this happened more often overall with these feature-based explanations. So I find this really interesting because I think it raises a lot of questions about what knowledge we assume models to have and how clinicians understand this idea of explainability. So explanations may be persuasive and actually increase the uptake of incorrect outputs. So not surprisingly, that's a pretty big problem for ethics because we want clinicians to use a model when its predictions are valid and reliable and not use the predictions when they are not valid. And as the saying goes, all models make mistakes, but some are useful. So it's also worth thinking about, are these explanations actually reliable? And so this was a really interesting study that was done a while back. And what they did here, this was a number of different methods of trying to provide an explanation for the prediction of what this image is. So you see here, this is a bird, we have corn and a dog. And so each of these is a different model trying to identify features that are relevant to the prediction of bird. On the last column here, this is a simple edge detector. So all this model is doing is identifying where the edges are. And so you see, oh, that has the shape of a bird, and you see the corn there and the dog as well. And so the thing is, if we're humans and we're looking just at these pictures, we see the shape of a bird and the model has predicted bird. Our assumption is that the model is using the features the same way that we do. So we think it sees a bird just like we're seeing a bird, and we would presume that that explanation is reliable. And so people have pointed out that this is a problem because models don't compute the same way that we do. In the medical context, similar concerns about the reliability of explanations have been brought forward. So I think this came out a while ago, but has been officially published in Nature Machine Intelligence. So Supporta and colleagues demonstrated They looked at saliency maps, which is a pretty common explainability method in AI for imaging. And what they found is that explanations highlight both relevant and non-relevant information. So you see in this example here, the reference segmentation. This is what a radiologist would determine to be the significant areas of this scan relevant to the diagnosis of edema. And you see the purple here, which is the AI segmentation. So you see that the explanation here is kind of going across physiologic boundaries and isn't specific to each of those lungs. In this example, you see it's also highlighted part of the right shoulder, which really has nothing to do with airspace opacity. I'm not a doctor, but I'm pretty sure. And then you see over here with pleural effusion, it's highlighted one area, but not the other. And so what they also found was that the accuracy of these explanations was correlated with the model confidence in the prediction. And so what this means is our explanations are the most reliable and the most correct in the clearest of cases. So one of the reasons why this raises a problem for ethics is because clinicians, in one of our studies that we did not too long ago, they look at explanations as providing reasons for a given prediction. They look at them as appealing to some sort of higher level knowledge about what is happening with the patient, what is going on with the patient, and they're using them to try and understand if they should follow this prediction or not. And one of the things that they often think that explainability can provide is some kind of causal account of the patient's situation that they do not have access to. And so that is a big problem, particularly when explanations are less reliable in the same circumstances in which clinicians are more uncertain. So all of this to say, when viewed as a means to provide reasons for a particular prediction for an individual patient, explainability, post-hoc explainability is so far unproven, and it may introduce novel risks in a clinical context. So going back to that skin cancer prediction example, if a clinician's initial judgment, which is correct, can be swayed by an incorrect prediction, you're introducing a novel risk into the clinical context. Currently, there's no consensus-based explainability methods that can successfully and consistently provide an individual level causal account of predictions. And I know a lot of people are working on this. And again, this isn't to say don't do explainability. These are really useful methods. However, at the present time, we don't have any that are consistent and reliable. And so explanations aren't actually truthful in the sense that clinicians commonly interpret them. Generally, there aren't questions about explainability's reliability for clinicians, and they're not aware of a lot of these computational limitations. So we have a lot further to go on this. So it also makes me think about, why do we actually explain? And I was thinking about this because we actually have a study on explainability and asking clinicians their beliefs about it. And so this picture actually was during the pandemic. My 6-year-old, their bunny had gotten sick. And so you see them treating the bunny here. They've covered them with a blanket and put socks on the bunny's ears. And so my kid drew a picture because they said they wanted to explain to the bunny what they were doing and why. And so they drew the socks on the ears. They drew the bone because I guess that's why the bunny was sick. And so I said, you know, why did you draw the picture? And they said, well, I don't want my bunny to be scared. I don't want them to not know what's going on inside. And I want to tell them why I'm putting the socks on their ears. And so it really highlighted for me how relationally important these explanations are. And really, it's not just about conveying information. It's about sharing in the decision-making process and describing judgment. So it's not explaining how socks keep your ears warm. It's about saying why you put the socks on the ears. It's to justify a medical recommendation or decision by making that decision-making process available for scrutiny and accessible to the patient. It's for patients and families to understand that clinical reasoning and to provide their input as well, because sometimes the assumptions that might be relied upon, or even the data points that might be informing that judgment, patients and families might actually have a different understanding of that data and context and can contribute to that reasoning process. It's also to reduce a power differential. So historically, clinicians have all of the knowledge and training and hold that. And by making the reasoning available, it reduces a power differential by helping the patient understand. And so again, fundamentally, this is a relational endeavor. This is about things that are going on between different individuals who are dependent on each other, just as the patient is dependent on the clinician to treat according to advancing their interests. The clinician also depends to a certain extent on the patient by providing input into that decision-making process, by reporting their values, by understanding their context. And so the power dynamic thing is one thing that I want to drill down a little bit on. And this was a really great article not too long ago by Collaboratory in Nature, where they asked, don't ask if AI is good or fair, ask how it is shifting power. And so one of the things that I worry about with explainability is that it piles even more weight onto having knowledge about the algorithm in the presumption that this is how we get to better informed clinical decisions. And so you're continuing to pile a lot onto a technology that is already very complex and not generally accessible even to clinicians. Patients and families also generally are more interested in the doctor's judgment, and this varies generally. We have some families, they want to know how all the monitors work. They want to know exactly how everything's happening, but for the most part, they want to know why a doctor's recommending something. They want to know, what are the risks? What are you hoping to get out of this? What do I need to look out for? And they actually want more weight on feeling that their values and their views are listened to and understood by the doctor. And so as we push more stuff onto the algorithm side of things, we only have a finite amount of time in a clinical context. And so as we're leaning more on the algorithm side, we're leaning away from understanding the patient and family better and devaluing their testimony within a clinical encounter. So going also to the point about transparency about a model output assumes that we need to know how a prediction is made in order to act responsibly. Professor London has already talked about this, how we don't always understand the causal structures, but we routinely use interventions that work. And what we do care about is the transparency related to clinical evidence. So if you were a clinician in a healthcare context, and you're using an AI-based tool to make a recommendation to a patient, you might tell the patient, well, we know this has been used in children. We know that it has, worked well at our institution. We know that using it has been linked with better this outcome. And so fundamentally, those kinds of explanations are not about how the model is working itself, but the relationship between the model and the world. And so explainability centers knowledge of the model, but clinical evidence centers knowledge of patients, processes, and people. And I think that this is where we need to be devoting a lot more attention for ethical AI in medicine. So just to give the key messages again, explainability, I think, can enable understanding of the model's operations as a system, very useful during the development stage, but we don't yet have sufficient evidence of current explainability methods' abilities to faithfully and reliably explain an individual level prediction. It also does not necessarily prevent clinicians acting on incorrect outputs and may actually increase the uptake of incorrect predictions for some. Explainability may be the most reliable in the clearest of cases and less reliable in complex cases. And due to these facts, explainable AI does not ethical AI make. We need more research to understand the influence of explanations on clinical judgment, and clinical evidence is a more reliable empirical foundation for basing clinical judgment. So with that, I will say thank you very much. And I think we've got a good amount of time for questions. So I look forward to chatting with you.
Thank you, Melissa. Thank you, Alex. Alex, feel free to turn your video on. For the Q&A portion, I'm actually not going to share a background slide. I have a slide that says Q&A, but I think it's a little bit more engaging if you can just see us and no slides, unless there are specific questions people have about slides. I will still be looking at chat and Q&A. I've taken some of the questions and kind of prioritized them. So in general, I'll be moderating the Q&A and asking your questions for you. But in some cases, I may ask folks to, unmute and be able to talk, and I'll allow you to talk in those settings. So first question I think I wanted to ask, so a little bit of background, when we talk about model explanations, we think of both global explanations and local explanations. And Melissa, I think you did a really great job of trying to differentiate the two. But I think restated, global explanations provide an overall sense of how much weight a model gives to a variable and to its values in general. And local explanations provide an explanation for individual model predictions, like why does the model think a given patient is either high risk or low risk? And how we derive these global and local explanations and how faithful they are actually depends on the types of models we use. So for example, Dr. Ewald-Steyerberg in chat pointed out that regression methods are quite explainable and perform similar to fancy machine learning methods for many medical examples, particularly those that deal with traditional two-dimensional biomedical data, not imaging per se. So he questions the desire for AI ML approaches as opposed to tools that are explainable out of the box, both on a global and local way, without these issues of unfaithful explanations, or much less of an issue. So the question I have is, when you offer the critique of explainability and the role of explainability, is your critique primarily about global explainability, local explainability, or both? And to add in Dr. Steyerberg's question, shouldn't we just be using regression whenever possible to kind of take the advantages of regression?
I can jump in on that one because I feel like, so I'm global explanations, global explainability, I think I understand from developers is a really important part of development of a model, querying the model, verifying certain assumptions about how it's working. And I think that those kinds of things, those are more research questions. Those are pertaining to understanding the relationships within the model and about the model. When we're talking about post hoc explainability, that is something that is different. And I'm not against it, but I do think that it is very problematic to assume that it is necessary for clinical practice. And I see, there's a lot of kind of opinion pieces or even, ethical guidance documents that assume that explainability is necessary, that say that it is necessary for practice. And I think that is an empirical question, because ultimately we need to use what is best for patients. And I think that also goes to the point about, should we just use interpretable models? I know Cynthia Rudin has a great paper on that. And I think that our commitment to furthering patients' best interests, again, is subject to that empirical standard. If an opaque model is the most efficacious in terms of impacting beneficially a given clinical outcome, then the evidence is there that we should use it. If a more interpretable method is able to provide that same clinical benefit, then I guess you could question, should we use something that's interpretable over something that's opaque? That would then depend on the extent to which clinicians might be inappropriately influenced by transparent predictions. So really, I think there's a lot more that we need to kind of understand about that human-computer interaction component to better support that decision. So I'm not against it. I'm just saying we need more research here. And I kind of reject the implicit assumption that ethics in AI or explainability is necessary for ethical AI.
I think the only thing that that I would add to that, I certainly think that, and Cynthia Rudin does make this point very well, that there's no need to use opaque models or overly complex models if simpler models will do. And I think there's interesting sociological questions about what the allure is to more complex models, if in fact you can sort of do equally well with something that's simpler and perhaps less sexy. But the other thing I think is, I'm not sure there's a one-size-fits-all answer to this question either, because if the task that you're doing is just a prediction task, it seems perfectly reasonable to me that in a very rich data set where you've got a system that's using very complex statistical relationships between lots of parameters, that you like a priori, you shouldn't think that you will understand what features it's using to make a prediction, or even that they're going to be sensible to you, since if we're just making a prediction, it seems reasonable that the system could use causal effects rather than causes, and it could use complex associations between causal effects rather than causes. So I think that there are kind of, I worry about some of the assumptions that are built in terms of understanding a model that and the desire that will give you insight into the underlying sort of cause of what's happening. And I think there's just a disconnect too often between what our models are doing and what's happening in the real world.
Thanks. And, I want to give Dr. Steinberg a chance to reflect. So I'm going to press the button that will enable him to talk. But just as an introduction, I think we're delighted to have Dr. Steinberg in the audience today. He is a world-renowned expert in clinical prediction models, wrote the textbook on clinical prediction models, the second edition of which was published in 2019, and coincidentally is giving a talk virtually at University of Michigan on Friday on the topic of statistics versus machine learning, friends or foes. So I thought this was a perfect segue into just introducing that there's another opportunity to hear him speak for a full hour. But Dr. Steinberg, what are your reflections on kind of what you just heard?
Well, thanks so much. I think this works now, right? Just to unmute.
Yes, we can hear you.
Yeah, thanks. Now, these were both excellent talks. I was really thought-provoking, as I labeled them. I really enjoyed listening to them. Fortunately, you don't have to listen to my double Dutch for a full hour. But just some reflection on this explainability. I recognize that, yeah, this comes up really often now if people talk about AI and machine learning. So I really like these critical reflections on the place of that word. To me, it always resonated a bit with the transparency word as a keyword, and that again links to my question on regression modeling, which are usually specifically the models that we know, framing M type of models or predict modeling cancer or whatever favorite model you may think of. These are usually relatively simple regression-based models. Now I recognize that the trend in, for example, in EU funding here in Europe, but also NIH funding, I guess, often we need to use these terms like, yes, we will employ machine learning, we will employ AI. We want to go this new direction. That was kind of my philosophical question, and that was already addressed briefly in an answer. The newness, something new is better than something old in a sense. So transparency is anyway, I think, a good thing to strive for. And that may also be at the basis of this, in one aspect of this explainability discussion, that we at least know what is going into a model. The machine learners have thought of some measures that do reflect what's happening also for individual patients. They like these Shapley values. I see them all the time. But nevertheless, they are, I think, overall, they are overambitious. I'll expand on that tomorrow a bit, that they promise more than they can deliver on, and trying to solve problems that were not addressable, not solvable before. I don't think that is really the truth, but having some transparency there are attempts. And to give you a final point, just some reflections now, but the final point is on the COVID situation, that we did this review, and one review was already presented, and that was on the imaging studies, I believe. We also did a review more general on any, say, prediction model in COVID. We did something like 600 that we reviewed, and most are really, yeah, terrible in a sense, very small data sets. Really think, well, why was this published? Who can work with this? And often they employed machine learning or AI type of approaches. Very small data sets, 20 patients had pneumonia. We still want to identify which were these patients. So there is this, yeah, whole issue of the newness of AI, machine learning that I'm struggling with. And I think, yeah, the issue of explainability, I really enjoyed the reflections that were presented in the two talks thus far. Thank you.
Thank you, Dr. Staberg. You know, the issue of transparency that Dr. Staberg just brought out was something that both of you had also touched on. And I wanted to highlight, you know, in 2020, there was this Health Affairs blog post by Dr. Sarah Murray, Bob Wachter, and Russell Cucina that addressed a no-show model that they were considering implementing. And what they wrote in this blog post was, as we considered applying the no-show model at our institution, we identified several layers of potential bias that might harm vulnerable patient populations. First, the potential for explicit discrimination was obvious because the predictive model included personal characteristics such as ethnicity, financial class, religion, and body mass index that, if used for overbooking, could result in healthcare resources being systematically diverted from individuals who are already marginalized. You know, the authors were only able to know this information because the model developer was transparent with clinicians about what went into the model, what were the variables included in the model. So I think, as Dr. Staberg pointed out, and I think as you kind of alluded to, and what I would say is, I would argue that transparency about which variables are included is super important, even if we don't know or we can't know how exactly they're weighted. So I guess, what are your thoughts on transparency as it relates to explainability? Do you view them as kind of independent concepts, similar things? Is one an instance of the other?
Yeah, I think that, so I think that for something as complex as AI, there are going to be a number of different informational strategies that each serve different goals. So like one of the things that has kind of gone toward helping with this sort of responsible use of AI are the model fact sheets, which was originally developed by a group at Google and Mark Sendak at Duke for the health context. So those kinds of things, they are really valuable, again, about knowing what goes into the model. And those kinds of things can help address certain kinds of questions. Like, you know, if I have a patient who has trisomy 18 and also recently underwent a heart repair and they now have chronic lung issues, how likely is the model to have processed a patient's data along those lines? Would it make sense to think that that patient's kind of patterns would necessarily be represented in this data? And that might help you know that or not, because if you see the data inputs that go into the model, you'll be able to see what kinds of things are there. You might also know anecdotally, you know, I know that I have 1 out of 5,000 patients like this who come across a year, so maybe the model doesn't work as well in those specific cases. And so that addresses a question that a clinician might have about how well their patient, how well the patterns that might be relevant to the patient are captured by the model in the prediction task. But it doesn't tell them what they should do on that basis necessarily. And that's something that's a little bit different, because the jump that happens, the kind of is-ought gap that we have with explanations to action, is that people take this description is valid of how this model got to this output. And so this is what we ought to do. But the ought actually requires a larger system of thinking beyond just the model's output itself. It requires, you know, patient values. What is feasible in this context? What does the unit look like today? Is this something we can do right now? And I'm thinking more of the ICU context, particularly in this example. And even that to your other point, because your other point was about bias. And so we can measure how a model performs on different demographic characteristics, on different groups. That doesn't necessarily mean that the actions taken on the basis of those model outputs are fair. So if we're continuing to focus on describing the model's outputs, we're totally neglecting this other side of the story, where we need to know if we are actually treating patients fairly or not, because you could see a model could be completely unfair, but a clinician could make a very fair decision. And that's actually what happened in that Impact Pro example, in the category of patients where the model didn't automatically refer, but made a recommendation. A larger number of patients who are Black were referred for care because of physician choices, that would have been if the model had been acting in isolation.
Alex, any thoughts on transparency?
I would just add that, so I'm a big fan of transparency. I'm not sure that transparency should be equated with explainability or interpretability. And I think that's because explainability and interpretability are specifically, or at least, a lot of the literature treats those as specifically about the model. And whereas I think, as Dr. McCraven just said, understanding your data set is really important. It's provenance. So a bunch of the issues with efforts to, diagnose COVID from radiographs were about the provenance of data. What's the ground truth of data? And, I think there's a background issue that I find fascinating, which is there's an allure to AI tools and machine learning tools that makes it seem like we maybe need less domain knowledge in order to use the tools, because they're artificial intelligence, they're going to find patterns in our data for us. But a thing that's always been impressed upon me is how important it is to bring your domain knowledge to the data sets that you have before you do any kind of analysis, statistical analysis, machine learning on them. Because oftentimes just by discussing the data, and this is what sort of the data cards and things get at, but is, what are potential confounders, who's not represented, and how would you stratify, all sorts of questions that bring to bear background knowledge. Those being transparent about those things, and then being able to say, how is your model going to deal with these things? Those are all questions that you can ask and get a pretty deep insight into before you do model development, and that should really shape model development. The other thing I would say about bias is bias can arise in all kinds of places, right? From the beginning of data gathering to the way that you frame the question you want your model to solve, to issues in sort of what are the social dynamics that are going to lead patients to be in your study, to, we have a lot of algorithms where the outputs might be correct, but then we correct them. Or we alter them, right? So bias in this process can happen in lots of places. And I think what's great about transparency, and what I think we need more of, is the ability to take a kind of whole technology view and say, how is it that we're taking steps to mitigate bias, not just sort of in our model and the way, and the way its outputs might reflect what we think are the ground truth in our training set, but in the way that it would be designed and implemented through the life cycle, so that we are sure that its actual impact on patients is going to be what we want it to be.
Thank you. I think those are great points that both of you made. In chat, Safa Jabri asks about the implications of AI explainability-induced errors. And I think both of you kind of alluded to the fact that explainability isn't perfect and it can, result in errors. So the questions she asks are, what are some of the areas of research that may help address this problem? On top of that, something else I want you to think about is this. One thing I think both of you raised is, and I remember Melissa, you specifically saying it, was that, in one case, it was good that they didn't present the explanation because the explanation might have led to false trust. But if, as a clinician, I saw a nonsensical explanation, that might actually lead me to appropriately say something is wrong. That's not the most important thing by a mile. So that might actually be a useful way to troubleshoot. So I guess overall thoughts on AI explainability-induced errors, and could AI explainability-induced errors be a window into actually troubleshooting models when they go wrong?
Yeah, there was actually a really neat paper that I literally saw on Twitter this morning, which was using failure cases as a source for qualitative analysis. So trying to understand why the model went wrong in those contexts. And I think that's a really neat area of research. And so I agree that, understanding where model explanations are failing to conform to, what we understand, you're sort of the matching process between the algorithmic processing and the clinical reasoning processing. I think it's a really interesting area of research. And to kind of the first point, so human factors analysis is one of the fields where we can understand this human-computer interface. is another. And so, there's more and more researchers who are looking at how people interact with technology, how we can be nudged, or how framing effects can influence our responses to them. And I think these are really, really interesting questions. And I think that one of the other ones too is looking at beliefs about technologies, which might be, there might be any number of reasons why these beliefs might be present, but someone, I think a couple of folks have brought up the anthropomorphization and why this happens with AI, and is that potentially influencing some of this? So I think that looking at these types of explanations and how people respond, again, I would say it comes down to an empirical analysis where we want to be looking at a net benefit, because that's what we're hoping for here. If it were the case that a model was able to present explanations in a way that enabled people to accurately detect which outputs were valid and which ones were invalid, then great, that'll work. But so far, we don't have enough evidence to know how reliable they are in a given situation.
Yeah, and how accurate are you going to be at detecting what's a sensible or a nonsensical explanation? Probably will depend on your background assumptions about what can AI models do. And in a kind of unhealthy knowledge ecosystem where people have inflated expectations about what AI models can do, it may be the case that any type of explanation can be kind of wedded to some background set of like, wow, maybe there's something I didn't understand here. So I'm not so sure about that. But I just have a deeper worry that that we're still sort of looking to see whether there's some internal coherence to the model. And maybe there's use cases here that we need to differentiate where you're like, I think this model is valid and is going to be really accurate for most cases. But how do I know that this is going to be one of those cases? Is there something I can do to try to detect whether this is one of the cases that sort of isn't covered? I suppose that's a possible use case for this, but I'm just not sure how much of that we can do from kind of the internal coherence of the model and the way that its outputs are generated from its inputs. That's why I think there needs to be a lot more conversation about validating models prospectively under the kinds of clinical circumstances that they're going to be implemented in, because we know that their performance is going to change in those circumstances. I'm not saying that in the development process, the iterated learning as we see that isn't going to be valuable. I just think let's put more stress on the value you get from that iterated learning rather than sort of always looking at how much more knowledge can we eke out of, or how much practical benefit can we get out of, more intricate knowledge of the algorithm itself.
Yeah, so I want to talk a little bit more of that internal incoherence and touch on the question from Jordan McKay. And I'll give some context around his question as well. So, Jordan McKay asks, communication-wise, how can we present abstract or less explainable AI decisions in an honest way so that lay people won't ascribe unearned anthropomorphization to the algorithm? And I think that's what you're touching on, is that may not be actually possible, but I'm curious to see what you think about it. But this is a really important question because earlier this month, the White House Office of AI released a blueprint for an AI Bill of Rights. And they highlight 5 rights that U.S. Citizens, people who live in the U.S. should have in terms of the role of AI in their lives, not just in health, but throughout all sectors of the economy. And one of the 5 rights they say is around notice and explanation. So here's what they specifically write. You should know that an automated system is being used and understand how and why it contributes to outcomes that impact you. But more specifically, they say it should also provide explanations as to how and why a decision was made or an action was taken by an automated system. It should be tailored to the purpose. It should be tailored to the target of the explanation. It should be tailored to the level of risk, and it should be valid. And what they mean by valid is the explanation provided by a system should accurately reflect the factors and the influences that led to a particular decision. So it seems like, from what you guys are saying, this may not actually be possible to do this in an actual faithful way. And I think, Dr. Stadberg alluded to, Shapley values is one way people have tried to offer local explanations for why a model said that a person was high risk or low risk. But there are lots of instances where Shapley values, quote unquote, fail, depending on how you define failure. So I guess going back to Jordan's question, Jordan McKay's question, what are your thoughts on, can we present less explainable AI decision systems to lay people in an honest way? And feel free to, I'm actually, after you respond, I may ask Jordan McKay to just weigh in on, is this question more about describing the model or describing a specific decision? But why don't you go ahead and answer that, and then I'll unmute to allow for additional discussion.
Yeah, so I think it's really interesting because similar kind of things came up with the GDPR, which is, so you have a right to an explanation. That's great. But if you were the person, so let's say you're on the receiving end, you're being denied a credit card, and the company gives you a reason why. Here's how the algorithm processed this, and this is, valid for these reasons. Let's say that you are in a heterosexual relationship and you and your spouse both apply, and you're told, well, the algorithm gave you a lower credit limit because you're a woman. Is that satisfactory to you? Probably not. It's the process that people want access to following that prediction to actually be fair. And it doesn't necessarily matter whether you know exactly why. So we might know the model function as a whole might systematically under offer credit to women, which is another thing that has come up in the literature with particular credit cards. It doesn't really matter if you know if that applies to yourself or not. What we're really looking for is the opportunity to redress some of that unfairness. So whether there's an opportunity for someone to review that decision and consider this individual case. And I think that the same thing is true in medicine, where you can have the reasons behind a given prediction are somewhat secondary to the actual decision to be made about it and its ethicality. So just as an example, if you have, let's say you have a model where it's predicting that a person is at risk of suicide, and let's say that their risk is really, really low, according to the model, based on whatever inputs that you have. But that patient is in front of you and is telling you, I am really distressed. I am ready to kill myself. I have a plan. I have all of these things. Let's say you know everything about the model. It's perfectly transparent and you have an explanation that is reliable and good. Does that override the patient's testimony? Does that override what you might perceive as being in the best interest of that patient? And is that which is the most important piece of information to you to actually make the decision itself? Is it the patient who's telling you that they're in distress and you needing to act on that? Or would you override that in favor of an algorithm that prediction is valid and et cetera? So I think that the kind of separation of the computation process and the actual decision, which is made on more factors than the computation process, is really, really important and is part of that reduction of anthropomorphization that Jordan is talking about there.
Yeah, I think that's a really important point, that for most points, AI systems outputs are an input into some larger clinical decision process. And, I sort of had, one of my sort of towards the end of the talk was like, what do patients need to know? Part of what they need to know is like, what's the indication for using this on me? And then why should I believe it works? And a lot of the problems out there are that we don't have real good evidence that we should think that this system works. And it's less that it's opaque. And it's more that you're asking me to trust you for something that's really high stakes. Why should I do that? You know, I think of Theranos as an example where it's like, here's a box and it's going to be able to do all these wonderful diagnostic things for you. And people are like, I would love to have a simple box that could do all those things. Show me the evidence that it can actually do those things. I don't want to have to trust in medicine. I want the data, you know, that shows me that it works. And if I have a system, you know, that's like, so some decisions are very outcome based. Some decisions are much more procedure based. And so like being denied a loan, there's a lot of procedure there where there are things that I want to know about whether I was treated fairly, whether I have diabetic retinopathy or not is maybe less procedure based and more like, are we going to be able to save my vision? And if the system is opaque, but I've got very good evidence that in patients, you know, like me, this is better than my clinician, then the fact that I can't understand how it arrived at that decision, but that I understand I'm at high risk and I need this diagnostic procedure and this is its sensitivity and specificity, that to me is an explanation.
Thank you so much. I think I'm going to move on just on to the wrap up. I know there's a lot more questions both in chat and in the Q&A. So we'll see if we can disseminate those questions to our speakers to kind of have you follow up on those separately and connect you with the folks who had asked the questions. I want to thank you again to Dr. London, Dr. McCrudden for coming and giving us really thought-provoking comments today in your talks. Thank you to everyone who's attending. Please be sure to fill out the post-event survey, and you'll see the link available as you exit the webinar. The webinar today was recorded, and so a link to the webinar materials will be placed on our Collaboratory website, which is posted here. But all of our prior events where we have permission to record, you'll see those events available for watching. I want to give a special thank you to our staff who done so much work to put this together. Lisa Ferguson, Kathy Kargianis, Lauren McCarthy. And I want to thank Christine Tashima for doing our live closed captioning. And I wanted to invite you to join our next LHS Collaboratory event, which will take place on November 8th at noon Eastern. The topic will be health equity reviews for AI in health and medicine. Our speaker is a phenomenal speaker. It's Dr. Khadija Ferryman from Johns Hopkins University School of Public Health. And the session will be moderated by Dr. Jody Platt and Paige Nong, who is a doctoral candidate at the School of Public Health at the University of Michigan. And we very much look forward to having you there. Thank you so much.